Hello and welcome back to the next installment of the Ray Tracer Challenge by James Buck, which I am going to implement in a language I've never used before, Rust, and yeah.
Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun.
We are coming along with this implementations. We are in the middle of chapter 2 currently, and we have left the implementation where we implemented a simple canvas like one which can, where are the tests? There are the tests. We implemented a simple color struct and we implemented a simple canvas. Where is it? Creating a canvas which can hold pixels of a certain width and height. And a pixel essentially is a color. So yeah, that's actually what we implemented the last time and wrote tests for. And we had to kind of wrangle with the language a little bit, or my understanding of it regarding on how we can be able to actually set a pixel to the canvas, which had to do with borrowing ownership and mutability and all those Rust concepts, which are quite new to me. So let's take a look. Actually, there we have a typo, writing pixels to a canvas. So yeah, let's fix this while we are going along. So what we are going to do now actually is I read over this in the evening after the last session, and I actually realized that our function, which we called write color, should actually be called write pixel according to the book. So let's change this. So this will be write pixel now. Okay, so it isn't able to rename it automatically. So then let's just search for write color and replace it by ourselves here. So okay, so this was one of the to-dos I marked out here. So now we have done this. Let's commit this. I'm not, it's quite early in the morning and I'm not 100% awake yet, but I wanted to get going with this. So no, we don't want to commit this. Yes, we want to commit this, and yeah, actually we want to commit this. So hit CI, renamed write color to write pixel to fit the naming from the book. There we go. So, and the next thing is I thought a lot and I read up about this mutability and borrowing and stuff and so on. And I came across that it seems to be a best practice for this simple data structures like we have here. Simply like something like 3 floating point values in memory or stuff like that. Something that has not a lot of specialty stuff in there, which isn't easily copyable to another location in the memory, to actually have it implement the copy trait, which then in turn allows the compiler to allow a simple bitwise copying of the structure to another memory location. So if we are moving it from, for example, we allocate it on the stack and we move it to another position, to another function within another stack context, it can easily be transferred there just by bitwise copying. And this is essentially what is happening then. And for these easy structures, like the simple structures which don't have references to something on the heap or stuff like that, it seems to be a best practice to do this. Once we did this, we can actually now remove this note here, and then we can, where is it? Where we actually, I guess, pixel add is it, which gives us a reference to a color, can now really give us a color. We should, of course, change. What do we need to change then? Yeah, we need to, of course, change the return value here as well, because now it can simply be transferred over as a copy, which is a lot cleaner than using this referencing stuff there. And we, of course, need to adapt our test. We don't need this dereferencing there anymore. We don't need this dereferencing there anymore. And there is another thing where we actually set the color, writing pixels to a canvas. Yeah, where is our write pixel function there? Actually, write pixel already took. Yes, because now we already thought about taking ownership of this color. Because we were using it and writing it into the canvas, which is quite nice. But as it is only a simple data structure, it can now be copied, which will be changed automatically by the compiler now. It will now be copied and not ownership transferred there. So this should work actually. Let's run the tests again. Cargo test. Oh, we now ran all the tests, but yeah, they ran quite nice, so that's okay. But we actually only want to run the canvas tests for now, which are 7 tests, and all of them passed. Okay, that's great. So we didn't actually break anything. This was one of the things I definitely wanted to change here. It is this copying trait for this color structure. Because what we can do now essentially is we could have maybe have this black as one color, which then can be copied over, but so we have a static allocation of one color struct somewhere and we could copy it over, but I don't think we want that at this point or need that at this point. Okay, so let's get going here. After we've changed this, I should commit it. Let's see. I have this. I've added this. I've added this, and I've added this. And actually, now we can do something which we couldn't before. If you remember the last session. We had this red color here, and we wrote it into the canvas at pixel coordinate 2 and x2 and y3. And then we wanted to actually reuse this color here in the assertion to make sure that the correct color value is at this pixel. And the system said, you can't do this because you've transferred the ownership of this color out of this scope into this canvas. And this makes perfectly sense. But now, as we have changed the semantics using this copy trait, we actually can remove this expected result here and use red here, and it should actually still work. Let's test it. And as you can see now, this works. As now, in this case, writing a pixel there is just copying this structure into the canvas, and therefore we have 2 color structures now in memory. One in the canvas and one in this in the stack of this function here, which is represented here, and we can use it here again. So this is actually quite nice for some trivial data structures like colors, for example. I will still leave this as it is because I kind of like it now better than just reusing this red. So we see that what is the expected one and what we are doing here a little bit clearer. So I will not change this. But yeah, let's commit the changes. So allow copy semantics for color struct. So one other thing I now want to do is actually, after learning about this copy thing, to take a look back at our tuple implementation and make sure we have it there as well. And that's actually something we did there because we simply copied this whole thing here, including something like partial equality, which we implemented later on from some documentation we found, without really understanding what happened here. So we have this copy semantics here as well, which is really a good thing for a vector or a point. So because this is a simple data structure as well. So yeah, so let's get going, adding stuff to our canvas. As I said last time, the next thing the book tells us to do is to implement something which allows us in the end to save our canvas, our pixel and color data to some sort of image format. And we are choosing the PPM image format here, which is actually a variant actually of PPM, which is so-called plain PPM. And the nice thing about plain PPM is it's simply string based. So it's just a certain amount of ASCII characters in a text file somewhat, which you can even though read line by line by yourself if you want. It's not some kind of compressed or complex binary format like PNG or stuff like that, which we might implement later on by using a PPM, a PNG library. But we want actually to implement this PPM because it is the format given to us in the book. So a PPM file actually, according to the book, always starts with a header, which is the simple characters P and a 3. So that's some sort of magic byte identifier for PPM, I guess. And then there is in the next line there is the width and the height, and then there are pixel information. So we are actually going to create our first test for it, as we did always before. We are creating a test and saying, okay, this one is called constructing the PPM header. And the scenario here is we actually have, I see, a canvas. So let's see, canvas new. It is supposed to be 5 by 3 pixels. And yeah, we are actually letting actual result is now c dot, let's call the function 2ppm, I guess, which should, I assume it should return a vector of U8s maybe, so simple unsigned 8-bit bytes. I guess that would be kind of feasible there. So the expected result then would be a vector. Can we actually easily, now am I going to do something strange? Can we convert string to byte array Rust? Let's just go and test this out. Essentially, what I think we want is something like is something like, if I understood this correctly, is string from. So now we are going to insert a string here and we say into bytes, was it? Yeah. So we are doing it this way, and now we have this header here, which is p3, followed by the width, if I'm correct here, which is 5, separated by a space 3, and then the third line in the document actually specifies, according to this, the maximum color value used. So we want to use color values between 0 and 255. So we are just, I guess we should write it this way, kind of. If we are later on, maybe we want this multi-line string, but I find this a lot more readable actually than having this strange multi-line stuff there. So let's create this. This is actually the header consisting of. Let's kind of explain what we are doing here. Because I will not know it if I look at it in a year or so. So we have this P3 magic bytes P3. They identify the document. Then we have width and height, 5 and 3. And then we actually have maximum color value. 0 to 255 is what we want, so we say 255. Unused doc comment node. What? Okay, it seems to me that there is something special with this, and yeah. So now what we want to do is actually assert equality between the actual result, as always, and the expected result. And of course this will not work because we haven't implemented 2ppm yet, as this is already telling us here. But we can actually implement it. And there is something I would like to implement, because I'm thinking about implementing different writers for this canvas. So I thought I may use something. I may use a trait for this and simply implement create a trait here called 2ppm, maybe 2ppm, like I guess like this. So, and define everything we need here. So let's define these fn 2ppm here, and it should return. It gets a reference to self, of course, and it should return, what did we say, a vec of u8s. Yeah, I guess this one would be a good thing. So now let's go ahead and implement 2ppm for canvas. Can I actually? Yes, I can. So I can have him insert the declaration here. Oh, we did not. Did we not implement vec? Oh, no, yeah, we did implement vec, but the auto type creation here didn't know we wanted it this way. So okay. Okay, so now what we can actually do is implement something within this trait, which is we can now have here a shared kind of function, which would be create PPM header, I guess, and it would which is given a width, which is a usize, and a height, which is a usize, and max color value, which is a U16, I guess. Why not? It's a usize. I don't really care. So, and it returns a vector of U8s. So, and this one, yeah, we now need to somehow construct this. So let's go ahead, I guess, and create us a new. Let's create a new vector, I guess. Let mute date header, I guess, is a vec new. And then we are doing header push value t, which would be the p3, and we want it. Can we do as bytes here now? This would most likely not work, would it? Can we? Is there a chance? I need to look. I need to read up on vectors. Append a vector to another vector. Rust. Best way to concatenate vectors. The structure vec has a method append. Ah, okay, I see. So let's see how this is going to work. So we created our new vector now, and I want to extend it now by having this string p3 followed by a new line, and I want this as into what was it? Into bytes. Okay, I need to do something like string from, and then make this into bytes. Would this work actually? Let's just try and return the header here. So expected struct U8 found unit type. No. Okay, this actually would work. The compiler doesn't. Okay, so that's quite nice. So let's now do. Is there a chance to get? There is something like string format, I guess. String format, maybe? No. String format Rust. It's a format macro. I guess we are doing something like string from format, I guess. Creates a string using Wait, no, creating a string, it says. So this should actually work then into bytes. Ah, okay, that's nice. So what we want here is we want the width and the height, and so we are just going to do this. We need the width and the height. We are getting it there. Width and height. So, and we want this followed by a new line. Yeah. And now we want to do and format again, like only this value, but as a string, and we want max color value, and we want it to be followed by a new line as well. So let's do it like this, and we're doing into bytes, and then we essentially return the header explicitly. Yeah, I guess this should work. I've actually done something wrong with the test. I haven't a new line here, and I should have a new line here. So now let's implement this. So we should now be able to actually call to get the header, I guess. Let header equal self create PPM header found for reference in the current scope. Okay, so can't I access a trait function? It seems to me that I can't access a function from a trait within the implementation. Is this right? Can it only be done the other way around? It somewhat would make sense to only allow it the other way around, but okay, so I think I don't want to think about it too much, so I'm just moving this function here for now, as we only have one of those implementations anyway. Method create PPM header is not a member of trait to PPM, not a member of. Okay, so actually this needs to be in here then, in the canvas implementation itself. Okay, that kind of makes sense, but because it isn't especially implementing the, I guess then we need a self here. Yeah, it expects 3 arguments, but if it's taking a self, can't it... Wait a second. Yeah, if it's taking a self, it can actually... it could actually do this a lot more intelligently, because it then can take the information from the from our struct, and we can simply hardcode the 255 there, because it's the implementation for our specific canvas. That should actually work out. So mismatch types, expected struct, vec, found. I see. Yeah, because we are not returning anything yet. So let's just return this header, I guess. And this should actually satisfy the test. Let's run the test and let's take a look. Yeah, it works. So it's correctly creating the header. Not perfect, because I really wanted to have this header structure within the trait. Maybe there is another way of doing this. Maybe having it in a module of its own or something like this. Yeah, this would most likely actually make sense, to just have a module which is called... That would actually make sense. Let's have maybe a module called PPM and then put those functions in there and then simply use them within the implementation of the trait of our canvas. Yeah, I guess that would make sense, but I'm not doing it now. But we may refactor this if we are creating another canvas in the future. I should try not to overthink stuff while I'm doing this. Okay, so we have this test. Now, the next thing, it's the way colors are stored within a PPM is actually more or less the same. It's let's write a test for it. It's essentially constructing the PPM pixel data. Yeah, constructing the PPM pixel data. So it's again 5.3 canvas. It's, let's see, we need, okay, no, I don't like this, because we now have, we will have colors. So let's actually have a color 1, which is color new, which is 1.50000, And we will have a second color, which is 0, 0, 0.5, 0, 0. And we will have a third color, which is a new minus 0.5, minus 0.5, 0, 1. So, yeah. Okay, so we have all these colors and we are writing them to the canvas. So let's write some pixels. The first color will be written to pixel 0, 0, C1. Let's move all this. And we want to write another pixel to position 2.1, which is color 2. And we want, oh yeah, pixel, there we go. Canvas, right, pixel 41C3. And we should write canvas the right way. So now let's format this. And then actually we want this to be a PPM. Cannot borrow canvas as mutable. Of course we cannot borrow canvas as mutable because now we are actually writing to it. So we need it as mutable. Okay, so now we will have, so we actually got the header and then we got the pixel data, which will be pixel data. And I guess I will just hard code this. So now let's go ahead and implement the writing of this stuff. Where the hell is my mouse? Where's my mouse cursor gone? My mouse cursor is... Ah, there it is. It was just not anywhere to be found. So yeah, we have our test now, so let's implement this. Essentially what we have done here now, we have the header and now we need our pixel data. So let's, yeah, I guess let's do pixel data, self, create PPM pixel data. Why not? So, and what we are going to return here now is a new vector. It's a mutable vector, it's PPM, and we are going to create a new vector here. And then we are saying PPM extend header and PPM extend pixel data, and then we are returning PPM. So yeah, of course there is no such method yet, so we need to implement it. Fn create PPM pixel data. It takes a reference to self and it will return a vec of type U8. So now we are going to output all this pixel data information. This shouldn't actually be too hard. We need different things for this, but let's for now let's just iterate our color or pixel data array. So for pixel in self pixels iter. Let's actually do, okay, we should first of all create a mutable pixel data vector here because we need to store our data somewhere. So now we are actually iterating, yeah, okay, so now we are doing pixel data dot append string from, we now have our pixel here, it's a color, yeah? So we should be able to do this, but this is not going to work. So what we need to do is, we need to actually put this color in range 0 to 255. So maybe I should create myself a function for this and call it get. Okay. First of all, we need to clamp it. We need to clamp it in the range 0 to 1. Yeah. So maybe it's time to implement something else on the color. Another operation on the color, because I want to be able to clamp a color. So let's do this. Mul color, partial equality for color. There's impl color. So let's put a public fn clamp functionality here, and let's say self, and let's take the lower bound, which will be of course an F64, and the upper bound, which will be an F64, and it will return a color. So essentially for each of the components. Yeah, so we are returning a new color, and we are returning a new color for each of the components. Let's do, let me just guess on how we are implementing min and max within Rust. So we will most likely have self red, and we want it to be, we want the minimum of red and our upper bound, so that we never can be above the upper bound. And we want the maximum of this value with the lower bound, so that we can never be below the lower bound. So yeah, and we are doing this for red, green, and blue. Let's write a test for this, even though the book does not have us implement such a function. Let's say no, let's say test, and let's fn clamping colors. So let's just create one. Let our color be color new, which will be 2.3 minus 6.7 and 0.8. So, and now we have let expected result will be a color, which then should be 1.0, 0.0, and 0.8. Yes, and let actual result be color clamp between lower bound 0.0 and upper bound 1.0, which I would very much like as some sort of default values for this. I have to take a look if there are default values for Rust functions. So assert equality, actual result, expected result. So let's run this. Of course, it will not. Oh, it doesn't even compile. Damn it. So let's first of all make it compile again. Yeah. Yes, I understand. So let's just return pixel data here for now. Yeah. So only one failed, and the color clamping works. So okay, let's commit this one. Yes, this one, and no, not this one, but yeah, this one, and the other ones we don't want. Git CI, implemented clamping of colors. So now we have this, and now we can actually should we actually implement it on a color to project it into a different range? I actually like this. But it could essentially be another, another type. So yeah, so no, I guess we won't be doing this directly on a color. So yeah. So let's implement this here in our pixel data function. So now let's get yeah, let's do it step by step. Clamped color. So let's first of all get the pixel to be clamped between 0 and 1 to make sure we have nothing there that is kind of strange and isn't. We can't really transfer over there. So now let's just project those values into the range of 0 to 255. Like we want an R, which is a U8, and this one will be clamped color. Essentially times 255, but I'm not sure that it is working this way, is it? Cannot multiply canvas, no, clamp color red to the, because I guess this will not work, no. So what we need to do in the end is we need to multiply this with, I guess, 255 there, and then we need to remove any kind of, how do we convert a floating point value in Rust, cast it into an integer? Rust convert floating point, there was it already, float to int. So there needs to be a way to do this. Of course we are losing the decimals then, but we really don't care. So first of all, this is not true. To round a real number is return the nearest integer. You just convert it to int with the discards all the non-integer parts. That's essentially what I want to do. Okay, I can simply cast this one. I see. So we don't want to round. Actually, we just want to lose the... Do we want to round? Yeah, actually we want to round this. Mismatch types. Round and then as U8. Because I know better than you. Okay, so... And if we do this, for red, green, and blue, RGB, we should actually have those values here now. And now we should be able to essentially do something like pixel data.extend, and now we can say make a format statement there, I guess, which has those 3 values in it. It will be a little bit harder because we need to somehow ensure that we have the right spacing between them and stuff like this. I'm thinking about having a vector of strings first, containing all the string representation of the numbers, and then later on building these lines from it, because there will be a second limitation, which is those lines may be a max of 70 characters long, and we need to count the characters actually and do stuff like that. Might be a little bit complicated. So yeah, maybe I should do this in another way. I guess I should do this in another way. So let's have a pixel strings vector here first, which I would like as a it should be a vector of string objects, I guess, and we will initialize it here. And we may be able to optimize this a little bit because we know essentially how long this will be, but or how big this will be, because we know the amount of pixels we have. But okay, let's now do this and insert for every pixel we have in our pixel strings vector. Let's push there a string. No, let's do a format which will contain the value of R. Let's furthermore push the green value there and the blue value. So now we should actually have our pixel strings. And as I said before, even though this is a little bit later on in the chapter, I wanted to do it first in another way, but essentially each of these data lines should not exceed an amount of 70 characters. And I actually need to take a look if there is another maximum amount of pixels per line, but no, it seems to be pixel characters, 70 characters, not 70 pixels, but 70 characters per line, and then a new line has to follow. So now we can actually quite easily write out this data because we know all this, we have all this information. So what we need for this is a kind of a, let's call it column count, which is actually a mutable use size, because we have a use size maximum within the canvas of data. So it's a mutable, no, wait a second, it's like this, a mutable column count with it, which is use size, and we initialize it with 0. So yeah, that's it. And now we can do for pixel string in pixel strings dot it, not iter. We want to do the following. We want, oh, we need to initialize pixel data now actually. So yeah, I'm not sure. Okay, let's do it here. Let pixel data be a vec new, but we want it to be a vec of type U8, just to make this working for us. So yeah, I was thinking about just constructing the whole string and then counting up the characters and checking if it would fit, but we can actually calculate it beforehand, just before we construct the string. So okay, so let's do this. Let's just let's create a mutable needed space variable here, which is a use size as well. So this would be 0 at first. And now we are going to check if column count does not equal 0, needed space plus equals 1. Because this is essentially now a space that we need there. So yes. Then unnecessary parentheses, so let's remove them. Okay, so if column count is not 0, needed space is added there, and needed space plus equals pixel string len. And now we can do something. We can check if we need to go to the next line. So if column count plus needed space is greater than or equal to 70, because or greater than 69, because I'm not 100% sure if the new line is counted as well. I guess not. So if this is bigger than 70, we need to go to the new line. So then let's just add pixel data extend. I guess this should maybe work. It's not, try calling chars or bytes. Okay, so it seems to me that we need to do this in order to and then into, what was it, not into string, into, was it into bytes? I guess it was into bytes, yes. So now we have this one, and cannot borrow pixel data as mutable. No, we cannot, because it is not mutable, but we need it mutable here. So so now we are going into the next line, and in this case resetting column count to 0, of course. And now we are actually writing the stuff. So essentially this we need as well, because in this case we will add to the pixel data another string from, we will add a space there into bytes. And then we will add pixel data extend pixel string into bytes. Cannot move out of pixel string, which is behind a shared reference. I see. Can we append it? Yes, I see. Pixel strings, however. Can we iterate in a mutable way over this? Mutable reference, note. So this actually does not work. How do I get the information from this pixel string thingy? Can I do something like this? Can I do a let just let data equals pixel string clone here? This should work actually. So now I have this data thingy here. Wait a second. This should work. I should be able to actually put this pixel, into pixel data, extend pixel string clone into bytes. This should work if I'm not mistaken. Yes, okay, this does work. So yeah, now we are finished, and the last thing we are appending as pixel data is finished writing is pixel data extend string from, and we put a new line at the end, 2 into bytes. So, and then we return our pixel data. Let's do it explicitly here. So this should hopefully work, maybe. Where is our 2ppm implementation? 2ppm. Where is it? There's the trade, there is the implementation. So it's essentially putting those things together. Okay, let's compile it and let's see if this actually returns the right thing. Okay, it does obviously not return the right thing. Why does it not? So what's the problem here? Constructing the PPM pixel data, constructing the PPM header. So now I've broken both? That's interesting. Okay, so let's start with the header. I guess there's a lot wrong with that because now it's putting all the pixel data into this thing. I need to only compare a certain amount of characters, I guess. Can I get a range of bytes from this? Something like a slice. Vector get slice rust. I only need a certain section of that with a start and an end. Okay, I can actually with a start and an end inclusive. Okay, that's kind of nice. Just with a start, just with an end. That's what I'm looking for, I guess. So what I need to do here actually is, no, it's, how is it written? Like this, I guess. So dot dot, and then what's the amount of characters I need here? Bytes. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we want in 11 characters inclusive. So this should, no, we are 0 indexed, of course. So is this at least now running? Okay, only one is failing now. Let's not call this actual result. Let's call this PPM image, and let's do an actual result is PPM image. And by the way, it's a reference to this slice, which is 11. And now we can do this here, and it should work. So okay, so now let's try and find out what's actually the problem with this. It's kind of hard to figure it out this way. I would love to see this in a plain text, more plain text string format. Maybe I shouldn't have used a vector of bytes for this. But okay, let's try and figure this out. So column count is, oh, do we actually increment the column count somewhere? I don't think we do. Yeah, and that's actually the problem. If we are writing to this thing and we decide that it fits into the line, we of course need to add our needed space to our column count. Otherwise it will always stay 0, and this is why it is not actually putting the spaces in there. So okay, this looks a lot better now, but still does not match. It is exactly 1 character too long. We have a certain bug here somewhere.
which is inserting a new line at before the first pixel is rendered, but this doesn't make sense. So essentially, this one here comes into play. Of course it does. Because we updated the column count before and then we checked it, and this makes, of course, insert it a space here. This method is kind of, it's not fun. This method is not fun at all. And I'm sure I could do it a lot better. In different languages, I would split this up in different functions and do it a lot more intelligently. But okay, let's not worry about this. Let's somehow get this to work. I still have a lot to learn about Rust. So how are we doing this? A little bit intelligent, at least. So what we are doing here is resetting the column count. So the following code needs to take this into account, actually. Yeah, however, this is something we need as well to take into account. So we need to do something else. We need to do it this way. If we do this, we are adding to the column count because we have now written another character. So let's do it this way. Let's just increment it here, and then let's increment it here as well by pixel string len, as this is what we have currently written. So let's check this now. It will fail again, but it should now have the same character count, and it shouldn't, after the header, have yes, there is no new line anymore, space anymore. What I haven't gotten right until now is that there should be the structure, the ASCII structure of the pixel data should actually resemble the lines of the image. So we should have a new line after each line of the image. Or after each line we have printed out, we have a new line. Or if the line would be longer than 70 characters. So we are splitting it actually up on the 70 characters mark, or if we have just jumped into the next line. So let's do this. Is there a way in these iterators to get an index, or do we need to actually take care of this ourselves? Rust iterator index. Is there a way? Iterate over list, indices, and values. So, okay, it seems that we can just, we are getting a tuple here, I guess, and we can, yeah, okay. So, okay, that seems to be another syntax to do it. Looks like some sort of closure, maybe, if Rust has something like this. Iter enumerate. So do we need to call this? Yeah, maybe we need to, and then we can have this information. I would like that actually. So for I pixel string in iter enumerate. Okay. So now we should be able to do the following. We should be able to determine if we are let mut current row. It's a use size as well. And no, current, let's call it current image row would be right, I guess. So and what I want to do here now is I want to, let's call it last image row. And what I want to do here is I want to calculate the current image row. Yeah, so now if current image row does not equal last image row. Last image row equals now current image row, and I want to, where is it? Do this. I want to insert a line break, and then I want to, I want to jump into the next line here. Line break for each row. This is do not exceed 70 characters per line. And this is insert line break at the end of data. Not line break, new line. So yeah. So now let's run our test again. And it's still failing. This should not happen. I thought we would have fixed this by now. So now we actually have a line break here. Oh, yeah, we are creating a lot more line breaks than we should, because I haven't taken into account that we now have each color component in this array. Where is so it is we need to actually multiply this with 3, as we have three color components, and we should do it like this. We have 3 color components for each of these colors. So yeah, now it is working. So that's okay. That's actually quite nice. So now we have some sort of image output here. We are going forward with this. I guess the next test, if I remember correctly, yeah, the next test is actually testing that there is a split between different, if we would be farther along than 70 characters. So let's implement this test as well, and then I guess we are finishing this up for today. And the next time then we will actually be rendering an image with this. So we will actually be displaying some stuff. Even though I would have loved to have this at the end of this video, unfortunately my time for today with regards to coding is running out. So splitting long lines in PPM files is the test called. Great, so let's now commit the, no, I want to commit the canvas. Okay. I get at source canvas, of course. So git ci implemented PPM output generation for canvas. So let me push this. Yeah, so we now have the capability to store pixels in our canvas and to actually output them as a PPM, even though it was quite the odyssey to create this implementation, and I still don't really like the code of this implementation, but yeah, nevertheless, it according to our test, it creates what we want and it works as intended. So in the next video, we will then actually completing chapter 2 of our book, The Ray Tracer Challenge by James Buck, by putting all of those things we've implemented now to good use, by taking our vector and point calculations we have done in the first chapter, and our canvas implementation, which we have now done to actually render the trajectory of a simple, yeah, pixel, bullet, whatever, however you might like to call it, actually into a canvas and to display it as an image on screen. So in the next video, we will hopefully see our first
rendered image, even though it isn't a ray traced image yet. But we will go there, we will get there. So yeah, thanks for staying with me again and doing this journey of implementing the ray tracer challenge in a language which is in most parts kind of strange to me yet, but I will learn and I will get better, and I hope you have fun while I'm doing this along the way, and I see you next time. Bye!